right? We wanted to continue talking about internal resistance. Didn't work out tremendously well. We do want to apply our equations for series and parallel circuits, at least for resistors when we have them in series and in parallel. And then we want to draw circuit diagrams, right? So even though we only have like 15 minutes, 20 minutes, whatever, 10 minutes, whatever the heck it is, I actually think we can get most of the way through those two objectives. So a lot of this is reviewed. The combination circuit piece isn't so much reviewed from last year, but let's see what we can remember. So in a series circuit, right, the distinction is that there's only one path that the charges can take to get around the circuit. So one path the charges can take to leave our EMF source and then come back to it. And here I have 4 resistors that are in series with each other. To calculate the total resistance of a series circuit, we just have to add the individual resistances together, right? So the total resistance just is the sum of the individual resistances. Is that in your data booklet? Yeah. Mm-hmm. Yeah, but it's not labeled as series, right? Like just like last year, right? It's there, but you still need to know that that's for a series circuit. One of the really important things about series circuits is that since there's only one pathway, it's the exact same amount of current everywhere in the circuit. Right? So each of these 4 resistors would have the identical current going through them. Right? Very important distinction between series and parallel circuits. The other really important thing about series circuits is that the EMF source, right, it's the electric potential difference that's applied to the circuit gets divided up, right? So if we have like 9 volts here, right, those 9 volts are going to get split up between the different circuit elements. If each of these resistors is identical, right, then they each get 2.25 volts. If they're not identical, then they're going to get an uneven split of the electric potential difference. So let's say, I don't know, this resistance is like 100 ohms, right? This is like 5 ohms, and the other ones are 5 ohms as well. Anybody want to give me a 1 significant digit estimate on what the voltage drop across this one would be? 1 significant digit. All right, let me change the value slightly. 555 and 300 ohms for this one. Now a 1 significant digit estimate on what the volt, like how much of the 9 volts this one gets? 9. Yeah, 9, right. Because the higher the resistance, right, the more of the energy per charge is going to be used up as we get those charges through that thing, right? So the bigger the resistance, the bigger share of the total source's electric potential difference it'll get. Alright, so those are the 2 really important things about series circuits. The current is the same everywhere, and they split up the electric potential difference that the EMF source can supply to the circuit. Follow-up questions from anybody about those 2 really important aspects of series circuits? Okay, so our other type of circuit is, what do I have here? We already said this, right? So we can absolutely use Ohm's law to calculate the voltage drop of the individual resistors. I suppose that is an important thing to note. So we know the current is the same everywhere, right? But when we use Ohm's law, if we want to find the voltage drop of a single resistor, we would just use that one resistor's resistance, right? So clearly, if they have the same current, whoever has the biggest resistance is going to have the biggest product of current and resistance. All right, so let's take a quick look at parallel, and then we'll see what we have time for. So in a parallel circuit, right, the distinction here is that there is more than one way for charges to leave the EMF source and then get back to it. So right, if charges are leaving the EMF source this way, they have like 4 different ways that they can get back. Right, so we call those parallel branches of this circuit. Now a parallel circuit has different major characteristics than a series circuit does. So it's almost like the opposite. In a series circuit, the current is the same everywhere. In a parallel circuit, the current's going to be different everywhere, but each branch will get the full electric potential difference of the EMF source. So if this is a 9-volt battery, each of those 4 branches is going to get the full 9 volts, because really, we just have these separately connected to the power source. So the electric potential difference is the same for each branch. The current, again, is going to be different for each branch. That would depend on the branch resistance. So if we had, I don't know, 1 ohm, 2 ohm, 3 ohm, and 4 ohm resistors, right, the current for each branch would be governed by Ohm's law, right? So this branch would get 9 volts divided by 1 ohm. So this branch would get 9 amperes. This one would get 9 volts divided by 2 ohms. So it would get like 4.5 amperes, right? This would be 9 volts divided by 3 ohms. So how much current there? 3 amperes, right. So Ohm's law totally applies. We just have to be careful that if we're finding the branch current, we're just using that branch's resistance. All right. Other questions from you guys about each branch getting the full electric potential difference, or each branch getting its own unique current for parallel circuits? All right. We have like 5 minutes. We're even to 57. All right, why can't I ever keep that straight? All right, so let's actually go ahead and work through, hopefully we can actually work through both of these examples. If not, then that's fine. So we have a circuit that's going to have 3 resistors in it, right, and 6 volts worth of batteries. I would like to do some calculations when those things are in series with each other, and then separately when they're in parallel with each other. And I'm going to go a tiny bit fast, but I'll try not to go too fast. I do like to sketch these things first. I'm not going to force you to sketch them first, right? But it really helps me keep track of if I'm putting these in series or in parallel. All right, so first we're putting these in series, and we do have these 3 resistors, 150 ohms, 150 ohms, and then 220 ohms. What are we trying to find? We're trying to find the voltage drop across the 220 ohm resistor and the current through the 220 ohm resistor. So I think and I should maybe label the electric potential difference. I think the first thing we'll have to do is find the total resistance of this circuit. Right? We know that the current through the 220 ohm resistor is going to be the same as the current through every other piece of the circuit. We can't find that current unless we know the total resistance. So as a first step, I'm just going to go ahead and add those 3 resistances together. So what is that, 520? All right, so 520 ohms is the total resistance, the equivalent resistance, the effective resistance. There's lots of different ways to refer to that total resistance of the circuit. Again, to find the current, which we have to find before we get the voltage drop, the current is the same everywhere, and we use the version of Ohm's law that does isolate for current. So I need to know the total electric potential difference that's being supplied to the circuit, which is 6.0 volts, and I need to divide that by the total resistance of the circuit, right? It's going to be the total resistance that impacts how many charges can go around the circuit. So 520. Yeah, I would love some help in knowing what that answer is.
0.0115.
Okay, 0.011. Give me 2 more actually.
5.3.
5.3. All right, amperes. So that should have like 2 significant.
5.4.
Alright, so it should have like 2 significant digits, but you know, whatever. A very small amount of current, right? 12 milliamperes, because we have a fairly large amount of resistance. Now, the other thing we wanted to find out for this circuit was what is the electric potential difference across it? So how much energy per charge is used up as the charges move through that resistor? We are going to use Ohm's law for that. We're going to clearly use the version of Ohm's law that isolates potential difference. But we do have to be a little bit careful this time. If we want to find the voltage drop across just that one resistor, we need to be very careful that we use the resistance of just that one resistor. Alright, so the current through that resistor is the same as the current in the entire circuit. There's only one pathway, so I am going to use that 11 or 12 milliamperes that we just found. And then I'm just going to multiply that by the 220 ohms. We should get something that's in the neighborhood of like 2 point something volts. It's going to be a little more than a third of the total electric potential difference. So what's that?
1.5
Okay, so 2.5 volts. Perfect. That makes total sense. It's a little bit more than a third of the 6 volts because this one has a little bit more than a third of the total resistance. Follow-up issues from anybody on the two things that we calculated for this series circuit? Yeah, Jacob.
Can you divide the resistance for that part of the circuit by the total resistance and then just multiply that by the total?
Yeah, so Jacob is saying, well, wait a second. Can't we find out exactly what percentage of the resistance of the total circuit this has? And wouldn't that be the same as the percentage of the total electric potential difference that it has? Yeah, absolutely, you could do that if you prefer that way, yes. All right, any other questions about having those three resistors in series? Great, so let's put them in parallel. It looks like we can comfortably do that in our remaining time. So I am going to redraw it, and again, I'm not going to force you to. On my better days, I don't have to, but on my worst days, I probably do, or else I might solve for the wrong kind of circuit. I'm going to go ahead and label my electric potential difference. I'm trying to be careful to not call this an EMF. If this battery has significant internal resistance, then the EMF would be greater than 6, maybe 6.1, 6.2. So I am trying to use my wording pretty carefully. And then we have 150, right, 150 and 220. It's the same three resistors, we're just connecting them quite differently. And we still want to find the same two things. We want to find how much current goes through the 220 ohm resistor, and then what potential difference there is across it. This time, it actually makes no difference what order we find those two things in. Because what's going on in this branch is totally independent of what's going on in the other two branches. So, well, you want to do the easier one first or the harder one? Easier. All right, the easier one is to find the voltage drop across the 220 ohm resistor. Right? What is it? Yeah, it's 6 volts because each branch gets the full electric potential difference that the power source is supplying to the circuit. So yeah, it's just 6.0 volts. Boom, done. If you were to do the most common ROM calculation that some of you did last year, you would get an answer that was greater than 6, which is impossible. Right? You can't get a greater voltage drop than what the EMF source is providing to the circuit. Alright, so that's the easy one. The harder one, which is not hard at all, is finding the current through the 220 ohm resistor. Again, we need to be careful here, because in the parallel circuit, right, we don't have the same current everywhere. Right? The charges are only going to take one of those three branches to get back to the power source. So the 220 ohm resistor, its current has no, it's not impacted at all by the other two branches. So we want to use its potential difference, which is 6 volts, and we want to use just its resistance, 220 ohms. So what's that? 27? Great. So 27 milliamperes, which is quite a bit more current than we had when we put the three resistors in series. Miles?
If on one of the branches there were two resistors, we
Yeah.
have to find the
Yeah.
voltage level of one of them. Oh, you're right.
That's next. I mean, we're not going to get to it today, but that's the exact next thing that we want to do. Right, so Miles is saying, hey, wait a second. Right, fine, that's easy, I can do that. But then what do I do if there's actually two resistors? It's not a difficult process, but that is what we want to do next. Other issues about finding the current through the 220 ohm resistor or the voltage drop when we have these three things in parallel. Okay. So we have like 5 minutes. I don't want to actually try and address combination circuits in 5 minutes. I would want at least 10. You know what? Let's get a taste of it. All right? Then we won't really finish it until next time. Now, those are the two extremely simple cases, putting things in series or in parallel. But we can and do encounter situations where we do have some elements that are in series and then other elements that are in parallel. And the only thing we need to know in order to handle those cases is that we want to make a simpler circuit by combining resistors together. So let's go ahead and take a look at the case that Miles just suggested. Let's do two 220 ohm resistors on this last branch. In fact, it's really ugly, right? Let me make it nicer. So let's still have a 150 ohm resistor here. Let's still have a 150 ohm resistor here. But now we'll do our two 220 ohm resistors. On the circuits that you have for your project, most of them look like combination circuits, but every single one of them is a combination circuit. At least once we introduce the short circuit, it is. So this is something you have to be able to do for your project. All right, so what did we say? We said the only thing we need to care about is replacing multiple resistors that are causing this to be not series or not parallel with a single resistor. So we need to do something about this branch, because this branch is preventing this entire circuit from being parallel. So what do? We replace it with what?
440.
We replace it with a 440 ohm resistor. So I'm going to redraw this whole circuit. I got my 150 ohm resistors. I'm going to draw that third branch with just a single resistor now. All right, 150 ohms here, 150 ohms here, and now 440 ohms, right? So this branch has 440 ohms of resistance. It doesn't really matter whether, there's 2 resistors or 3 resistors or 4 resistors that are making that up, right? If we're trying to find things out about like how much total current leaves the battery, something like that, right? It's going to be the same answer whether we pretend that there's 1 resistor as opposed to 2. That's seriously all that we need to know to be able to handle a combination circuit. But combination circuits do come in like different flavors. So here's a different one where we have a single resistor that all of the charges have to go through, and then we have 2 branches, right? Some of the charges will go through this branch, and some of the charges will go through that branch, right? So what the heck would we want to do here? There are values here that you probably can't see. This one is labeled 2 ohms. This one is labeled 6 ohms. This one is labeled 3 ohms. So think about how you would go ahead and combine 2 things into one thing to make this simpler. Right? There were possibly different ways we could do it. But take 30 seconds and think about what you would combine to make this simpler. And then it'll probably have to be our stuff. All right, Christina, what are you going to do?
If I could, I think I would take out the 2 ohm resistor and then make the other ones 8 and 5. If that's okay.
Would that be okay? I need to give that some thought. That is definitely not what I would do, but that has some logic to it, and I need to think about that a little bit. What I think I would do is combine these 2, right? Now, I think I made an oopsie before and forgot to say how we combine parallel resistances, right? It's like that. I forgot to do that. But we can do that, and I think we even have enough time to do that for these 2 resistors, right? One of the resistors. All right, your homework. We'll pick back up with that next time. Page 9 of the packet, that's it. Page 9 of the Topic 5 packet, that's it.
There are 5 numbers, right?
What's that?